All right, today's going to be, I think, a pretty exciting day. At least I feel that way. I like this topic. Oh, I wanted to share with you all Desmos, right? I happened to be on Desmos the other day, and it turns out that Desmos just released a beta version of a 3D grapher. So if you go to Desmos, and you just click on Desmos, it says it right here at the top, introducing Desmos 3D beta. Try it now. So I started playing with this a little bit, and it's not terrible. It's not, okay, it's beta, right? So I'll be honest, I think I like, what's the other one? GeoGebra better right now because it has more functionality. But I think Desmos is just going to keep improving this, and I think at some point it'll be the one. So like here's an example of a surface, right? A surface and the cylinder, and then you can see the curve where they meet. The thing is you can't adjust the opacity. You can't like it's either solid or a little transparent, but you have to turn them off. And then you can see the curve where they intersect, right? See that? And then you can move a point along the curve, right? So it's cool. It's cool. There's certain things that I think I will like about it, but whatever. I just wanted to show it to you because it's there now. We'll see. All right, so what we're going to do now is we are going to shift to 11.7 maximum and minimum values of surfaces. And the first thing we want to do is do a quick review of Cal 1. And when I do this quick review, you're going to be like, well, thanks, that would have been nice if you would have done that before you gave us that mini exam. But I was hoping that you would have reviewed it on your own. So when it comes to Cal 1, when you're trying to find maxes and mins, we have two different scenarios. We have when you're looking at a closed interval and where you have an open interval. And what I mean by that is the domain. So if I take a function back in Cal 1 and define that function between 2 points, A and B, let me do a different picture. Let me do it this way. Do we all agree that that is a function that is defined on a closed interval, right? It's also a continuous function. I can draw it without picking up my pencil. In Cal 1, we learn a technique to actually find the absolute maximum, absolute minimum of a function. There's an actual technique, and on your take-home exam, you may have used this, all right? But there's one method for this, and there's a different method if it's an open interval. So if you have a function that's on an open interval, maybe it goes like this. That means it's not closed, right? It continues. Then we don't have an idea here of an absolute maximum, but we have what are called local maximums and local minimums. So this right here would be a local max, right? Local max. This is also a local max. And then we have this right here, which would be a local minimum, right? Here, this point here would be an absolute max. And the absolute minimum would be here. This all ring a bell? Cal 1? Ring a bell? Just the idea. So back in Cal 1, if we're trying to find the absolute max and minimum of a continuous function on a closed interval, what we do is we take the derivative, we set it equal to 0. We also take a look at that derivative and see where it's undefined or where the derivative doesn't exist. And anywhere where these two things happen, we call these critical numbers or critical points. Critical numbers are critical points. Do y'all remember what to do once you find the critical points when you're doing this? Plug the critical points back into the original function, and what else do you have to plug back into the original function? Not only the critical points, but also the what? The two endpoints. Okay? So what you do is you find the critical points or critical numbers, then you plug the critical points, CP, critical points, and the endpoints into the original function, into f, not the derivative, into the original function. And what you're looking for is the biggest value that comes out is your absolute max, and the smallest value that comes out is your absolute min. Does that ring a bell? Does that seem a little familiar to you? Okay, that's how you do it if you have a closed interval, right? Now, if we have an open interval, it's different. What you do here is same thing, you set the derivative equal to 0, find out where the derivative is undefined, right? Those are your critical points. But now what you do is something completely different, right? Because you don't have endpoints. What you do is you do like a number line and some sort of sign chart or something like that. You put your critical points here, critical point, critical point, and it breaks up your number line. And then what you do is you take these, test points, and what do you plug these test points into? Into what? Not to f, into the derivative. And if the derivative, if it turns out to be positive, that tells you your function's going up, and if it's negative, your function's going down. So what you can do here is you can figure out where your original function goes up and down and maybe back up by looking at the derivative, right? By analyzing the sign of the derivative, you can figure out where it goes up and down. And then from there you can say, oh, look, it went up and then down, so that must be a local max. And here it went down and then up, and that must be a local min. So these are the two different techniques. I'm not going to reteach these. This is really just for you to take like more of a step back look, that when we had a function on a closed interval, we got the critical numbers in the endpoints and plugged those into the original function, whereas if we had a function on an open interval, we found the critical points, and then we did like a sign chart for up and down. Two different methods, right? Okay, so what we're going to do today is we're going to talk about maxes and mins, maxes and mins, but of functions of two variables now, which we already know are surfaces, right? And so what we want to be able to do is find, if possible, the maximums and minimums of those functions. And we're going to have two different scenarios just like this. We're going to have the scenario where we're just looking at this sheet and we don't have a restriction on the domain, which means we're going to find little hilltops and valleys, which will be local maximums and local mins. And then we're going to restrict it to a domain, and then we should have absolute maxes and absolute mins. So I just want to make sure you understand we're going to have a complete, like what we did in Cal 1, exactly we're going to do that here in Cal 3, but with surfaces. And we have two different scenarios. All right, so here is just a reminder of, that'll work. This is a surface, kind of an extreme surface to show you, illustrate that you can have a bunch of little hilltops and valleys, right? We would be interested in knowing, what are these points? Where do they occur? How high? How low, right? When you have something, this is the picture out of the book, okay? It's, I think this is better, right? So this right here, each of these little tops would be a local max, local max, local max, local max, right? And then local min, and then all the places on the bottom here would be local minimums, right? And yes, we might have an absolute max. An absolute max would be the absolute highest point on the entire surface, right? And the absolute minimum would be the absolute lowest point on the entire function. So the definitions carry over directly from Cal 1. Everything should make perfect sense, right? No? This is just the definition of all those, right? What does it mean to be a local max? It means that everything around it is lower than it. To be a local min, everything around it is higher. So those are definitions. I don't want to get into those definitions too much. What I really want to get to is this, what's called the second derivative test. The great thing about the Cal 3 stuff is that when it comes to finding local maxes and local mins, we've got this test. And it's a super simple thing to do. We just have to crank it out, all right? So this test says, all right, first of all, let's suppose that you have, where's my yardstick? Oh, there it is. It says, let's say you have a function of two variables, a surface, right? All right. Suppose you have some surface, and suppose that the second partial derivatives of that function f are continuous, which means that in order for us to use this test, we must be able to calculate second partial derivatives. So as long as we can do that, then what we're going to do is we are going to calculate this value d. All right? We're going to calculate this value d. So what we do is we figure out this value of d, and if the value of d is positive, we're going to get a certain answer, and if it's negative, we're going to get a certain answer. So on the board over here on the side, off camera, I'm going to put what the calculation of d is. D is, okay, the way we write it is d of ab. So you have to calculate d at a certain point. And what it is the second partial with respect to x at ab, right? That's this, times this multiplication, the second partial with respect to y at ab, and then minus the partial with respect to x, then y at ab, whatever that quantity is, squared. All right, that's what we have to calculate. The result after we calculate that is one of these three scenarios. The first scenario is that if d is greater than 0 and the partial with respect to x twice at ab is greater than 0, then what do you have? You have a local minimum. This would mean we have a local minimum. For part B, if d is positive, right? D is positive and the second partial with respect to x is negative, then you have a local max. And if d is negative, you have a saddle point. It doesn't say it there, but I think if you scroll down, it'll say it. You have a saddle point, which means you're not at a local max or a local min. All right, so let's just do an example just so you can see how this is going to work. So you've got this surface, right? You've got this surface, f of xy equals y squared minus x squared. And there's a nice little picture of it for you. I'm going to zoom out. It's a little bit too big. All right, so here's our surface. Why is this so damn big? There we go. Okay, so there's our surface. And we want to see, there's no restriction on the domain here. So you have to imagine that surface continues in every direction, all right? I want to see if there are any local maxes or local mins. What does it look like to you? Does it look like there's going to be any hilltops or valleys? You think so? Well, there's only one way to find out. Let's calculate d. All right? Oh, you know what? I forgot to mention something. Hold on. Hold on a second. I forgot something very big. Hold on. Sorry about that. Okay. This right here, all of this to calculate d, all of this, you have to know what this point AB is. I left this out. This is a big deal. So this point AB, that point AB is a point where the partial of f with respect to x at that point is equal to 0, and the partial with respect to y at that point is equal to 0. So remember in Cal 1 that we found critical numbers, right? How do you find critical numbers? You figure out where the derivative was 0, right? Or where it doesn't exist. This is basically us finding where the derivatives are 0. And then once we figure out where the derivative is 0, we plug that point into this formula and get our calculation for d. let's do the example. I think once I do it, you'll see it's not as confusing as I just made it. All right, so there's our function, right? So my first job is to see if I can find any points that make my derivative 0. Derivatives, plural. I need the derivative with respect to x to be 0 and derivative with respect to y to be 0. So first let me take some partials. What is the partial with respect to x? Negative 2x. Okay. What's the partial with respect to y? 2y. Okay, now what I need is to figure out a point that makes both of those equal to 0. So if I say, okay, where is this 0, right? Then I'm saying, where is negative 2x equal to 0? Well, that happens when x is 0, right? But I also need this to be true. When is this equal to 0? Well, that means 2y must be 0, but that means y is 0. So the only point that I have, the only AB, the only critical point that I have is the point 0, 0. I have to let x be 0, I have to let y be 0, and that will be a point that I can check, right? Now what I need to do is calculate d at that point 0, 0. Okay? This is what we refer to as a critical point of this surface. I need to calculate d. Well, to calculate d, I need some more partials, don't I? So I may as well get those before I calculate d, let me get some other partials. What's the partial with respect to x twice? Negative 2. What's the partial with respect to y twice? 2. What's the partial with respect to x then y? Well, here's a partial with respect to x, right? Now take the derivative of that with respect to y. 0, because you're treating x like a constant. Right? Everyone understand those three? All right, so now what I do is I need to calculate d. d at the point 0, 0 should be, I'm just going to write it down so you see directly from there. What I'm doing is I'm taking the second partial, partial with respect to x twice. I'm plugging in 0 for x and 0 for y. Then I'm taking the partial with respect to y twice, plugging in 0 for x, 0 for y. Then subtracting from that the partial with respect to x, then y, plugging in 0 for x, 0 for y, and then squaring that answer and figuring out if this comes out to be positive or negative, okay? I know that looks terrible, but this actually is going to be super easy because what is the partial of f with respect to x twice? It's negative 2. Regardless, this is actually irrelevant, isn't it? This is absolutely irrelevant, but it will be later. For us today, for this problem, sorry, not today, for this problem, that's just negative 2, regardless of where I am, right? And then what's the partial of f with respect to y twice? 2, okay? And then minus, and then what's partial with respect to x then y? 0, and then square that. And so you just get negative 4 here, don't you? And what is the conclusion if we have a negative d? You have a saddle point. That's it. This surface has no local maxes or local mins. If you look back at the surface, what it's doing is it's kind of like in one direction it's going like this, right? And then in this direction it's going like this. And so you don't have any like hilltops or valleys. You just have this one point right at the origin, right? Right at 0, 0. What happens if I plug 0 into the original function? If I plug in 0, 0 to the original function, I'm at 0. So that's the origin, right? The origin is a saddle point. Do y'all understand where they get the name saddle from? Like if y'all see the saddle here? Yeah. Like if I were to step over like that, right? Saddle point. My legs are going down, right? And the saddle comes up. So that's not a local max or min. Okay, next example. How about this one? I'm not going to show you the picture yet, okay? I'm not going to show you the picture of this one yet. So people use different approaches on this. Some people are like, let's just get all the partials, let's just get all the partials first. You know, we're going to need a bunch of partials, let's just do them all. Some people are like, no, let me find the critical points first. I don't care. What do y'all want to do?
Partials first.
You want to do all the partials first? Let's see if it gets bad. What's partial with respect to x? 4x cubed minus 4y. Okay, let's do the partial with respect to x again. 12x squared. Do you all agree with that? All right, we're going to need the partial with respect to y. What's partial with respect to y? 4y cubed minus 4x. Y twice is just 12y squared. Do we need any other partials? fxy, so with respect to x, then y. So we did with respect to x. Here was with respect to x, so with respect to y now. Negative 4. Negative 4. Okay. Yeah? Those are all the partials we'll need to do the problem. So now, let's find our critical points first. So I want the partial with respect to x to be equal to 0. I also want the partial with respect to y to be 0. Anywhere that this happens, right, anywhere that this happens will be where I calculate d. Okay, set the partial with respect to x equal to 0. 4x cubed minus 4y equals 0. Oh, shit. Yeah, I'm not going to get a solution there, am I? Because it's a one equation, you have two variables. So there's an infinite number of solutions to that, right? How am I ever going to check an infinite number of solutions? Well, what I'm going to do is I'm going to look at the partial with respect to y, which is what? 4y cubed minus 4x. That must also equal 0, right? So if they must equal 0, both of them, then they must equal each other. So I'm going to set them both equal to one another. Maybe if I do that, I get something, right? 4y cubed. So now I set them equal to one another. What should we do here? How about we divide everything by 4? Yeah? Get rid of the 4s? No? Oh, I thought I said yeah. I thought you said ma. Oh, yeah. Okay, so divide the 4 out. We're okay with that? Let's bring everything to one side. We bring everything to one side, we've got that. Did y'all see anything?
I just see zeros.
You see zeros? What do you mean? Like 0, 0 is a solution?
Yep.
Yeah, I do agree. Is that the only one, though? Yeah, I think a 1 might work as well.
So 1 minus 1 minus 1.
Yeah, but we gotta solve it algebraically. We can't just go off inspection. Because you might miss something, right? Any ideas?
Group them and pull an x out.
Like grouping? You want to do grouping? You want to try grouping?
Times x minus 1.
So let's try grouping. Continue this. So you'd have to do this. X cubed plus x minus y cubed minus y equals 0. Is that what you mean by grouping?
Yeah, and then you need
And like pull something out of this?
yeah, you get x squared times
X.
plus 1, or x times x squared plus 1.
You can do that. I agree. And then can you do anything here?
You pull out a negative 1.
Negative y? And be left with y squared plus 1? Grouping doesn't work that way, does it? Don't these have to match for grouping to work? These have to match. Right? These have to be the same. It doesn't work. But it's good because we want to be thinking, what can we try, right? That doesn't work. Okay, so let's go back. Something else, maybe. Okay, these two right here. This is a difference of cubes. This is a difference of cubes. Now you have to know the formula for a difference of cubes, which is on your formula sheets if you've... Well, how could you forget it if you never memorized it, right? But you need to know the formula exists, right? So what is it? These two right here become x minus y times x squared plus xy plus y squared. That's the formula for difference of cubes. That's just the first two terms written factored. So that becomes these two. We still have over here what? This? Watch. How do I want to do this? I factored a negative 1 out of each of these. Why? Why did I pull a negative 1 out of these? That doesn't seem very natural. Or should I? Maybe I shouldn't have. Yeah, no, hold on. I have an x. What do I have up there? Okay, so let me just rewrite those. Sorry, that's my fault. Let me just rewrite those backwards. There, like that. I'm going to put in parentheses just so you can see what the next step will be. Pull out the x minus y. Pull out the x minus y. Okay, so what do we have here? X minus y gets pulled out. What are we left with? X squared plus xy plus y squared, what? Plus 1 equals 0. And now what? You can set this equal to 0 and that equal to 0, right? So you can get x minus y equals 0. And then the other thing is x squared plus xy squared, xy plus y squared plus 1 equals 0. This.
Shouldn't that x squared plus xy plus y squared be in parentheses?
We factored out, right? So right here we pulled this and this out, right? So we pulled that out as a single factor, and then it would be this, and then plus 1, right, to distribute.
My brain's not brain.
It's all right. X equals y. X must be y.
I think he just wanted that x squared plus xy plus y squared difference. Because then otherwise you would just multiply times that whole thing. The one would.
Where? Where, here?
Yeah.
Well, okay, it doesn't have to be, but yes, it could be like that. And then boom, it would hit that whole thing and then hit the 1. Yeah. But if you can take the parentheses away because there's not anything out here.
Yeah.
Yeah. Do y'all agree? Okay, now, this is tricky. This is tricky.
You can't just sub y for x since we know x equals y? Or
Well, that only solves this part, right? We can't sub it in here. We can sub it in over there, but we can't sub it in here. Let's see if we can convince ourselves whether or not this is going to have any solutions here. Is this going to have any solutions?
No. No, I'm just, like, if you put negative 1 on the other side, and you've got everything squared.
That squared, those have to be positive, but what about that though? Could that be negative?
I don't think so.
Well, x could be positive and y could be negative, and then it would be negative, right?
Yeah.
So it is possible, yeah? It is possible, maybe? How could you convince yourself whether or not that's going to have any real solutions? Do we know whether or not that factors? Where did that come from? Came from here, right?
Yeah.
Does that factor?
No.
No. If it did, then the formula wouldn't be this, right? The formula would actually factor those. So we know that that doesn't factor. This is still kind of an open question, right? This is still kind of an open question. Let's pause on this. Here, let's put the pause button here. Let's pause that for a moment. And let's just deal with this. X must be y. Okay, x must be y. So let's go back to this first equation right here. If x must be y, right? If x must be y, then I can now take this and say, okay, if x is y, which would satisfy that, then let's write it this way. That must be true, right? Replace the y with x. You could also replace the x with y. And now when I solve this, I can pull out a 4x, be left with x squared minus 1 equals 0, and you get x is 0, 1, and negative 1. So there, 4 times what would give me 0? I'm setting that factor to 0. Difference of squares, x plus 1, x minus 1. Set each of those equals 0, we get 2 solutions. Right? So continuing, you all right with this? If x is equal to y, then x must be 0, 1, or negative 1. We have 3 critical points then so far. Our critical points are this. If x is 0, if x is 1, and x is negative 1. Okay, if x is 0, what's y? 0, because we said that whatever x is, y is, right? That's the condition we're under. So if x is 0, y is 0. And then if x is 1, y is 1. And if x is negative 1, y is negative 1. So let's just recap what we've done. We took this, we didn't know what the solution was. We set that equal to this, right? And then from there, we got that equation, then we came to here. And the only thing we could really get was this, right? This we're still kind of like, I wonder if that has a solution, right? Kind of tough to see if that has a solution or not. But we said, all right, let's just stick with this and go and see what happens. Okay, so I'm looking at this and I'm thinking, all right, is this really worth our effort to try and mess with this? Or should we have really just maybe rethought maybe a different approach from the very beginning? You know, we said this was equal to 0, this was equal to 0, right? Maybe we could have tried something else because this is unknown. Like, not unknown, but not easy to do. What if in the beginning we would have taken this equation and solved it for, let's say, y? Do you all agree? Just move the 4y over? Divide by 4? Okay, so y has to be x cubed. Now take this, right, and replace your y with what? X cubed. So you get 4x cubed minus 4x equals 0, right? And now this is 4x to the 9th minus 4x, right? You multiply 3 times 3. GCF, 4x, x to the 8th minus 1 equals 0. What is this? I know, it factors though. Okay, yeah, I mean, you could just look at it. Let's do it this way. 4x equals 0. Set each of the factors equal to 0. We can do it that way. That's fine. So what's your only answer here? 0 and x to the 8th equals 1. Square root both sides. I'm not square root, 8th root both sides. When you do an even root, you have to do plus or minus. So this gives you x's plus or minus 1. And now I know that those are my only answers. Okay? These are my only answers. So what I'm getting at is you're going to have some flexibility and freedom on how you go about solving things. And you can see that the way we did it initially, we worked, but we weren't sure if we were done, right? But by doing it this way, we actually were able to get to some answers. I don't think there's anything left open here, right? I mean, like this is